Welcome, everybody, to Weekly Quantum World Detangled, Season 5, Episode 5. I am joined by my friends and sponsors, Denise, Ruffner, and Atom Computing.
Hi, everyone. Nice sunny day in Southern California. Very excited. I've been looking forward to this podcast all week. We're lucky to have today with us Chris Ferrie from University of Sydney?
University of Technology, Sydney.
University of Technology, Sydney.
Yeah.
So, Chris, you want to introduce yourself for a minute, please?
Sure. Yeah. So I'm Chris Ferrie. I'm an associate professor at the Center for Quantum Software and Information, University of Technology, Sydney, in Australia. It usually just is, most people just know it by UTS. It's got a really big logo on its big building in the center of the city. And when I'm not doing research in quantum software related topics, I write books. So mostly children's books, but also I'm now writing some books for older audiences as well.
Good, and you're calling from Australia, not from space, despite your actual physical green screen that you just explained to us that you have. You spent some time in the US and Canada as well. Give us a kind of the 1-minute rundown of who you are, where did you grow up, how did you get into physics, your little North American tour, and then back down under.
Sure. Yeah. Well, I can go backwards. So I'm an associate professor here at UTS, and before that, I was a postdoc still in Sydney at a different Sydney university in the group of Stephen Flomia. And before that, I was at the University of New Mexico as a postdoc with Carl Caves. And I did most of my schooling in Canada, where I grew up. So I was a student at the Institute for Quantum Computing in Waterloo for probably the plurality of my life. And I grew up around that area, and I've jumped around. I'm now in an engineering faculty. I was a postdoc mostly in physics faculties, but my formal training was in applied mathematics. So I've jumped around quite a bit. I often, it's hard to know. So it's hard to remember these things, and memory is always just a story that we we tell ourselves. So a good story, I think, is one where I tell people that I wasn't really ever interested in physics per se. I was always interested in mathematics and where it could be applied. So I love the idea of solving problems with mathematics. And physics was something I kind of just fell into. And it was a fun place where you could solve math problems. And that's kind of like how I got into it by accident.
Your LinkedIn says that you're a physicist, a father, and an author. Do those three have anything in common?
Oh, absolutely. Yeah. So people often ask, is writing children's books, like, how different is that than communicating with physicists? And I say that I don't really see them as different audiences. So people just want to hear interesting stories, and it's one of the things I've tried to do when I communicate my research, in conference talks or even just in papers, is make sure that these are things that people want to read so that the message can get across.
So how do you do that? I read a quote from you that said, I grew up in a small farming and manufacturing town in Canada's industrial heartland. Boys did things like play sports and video games. They definitely didn't write. I presume not many of them did physics or math. What is that language to explain things to kids or scientists?
I think it really depends on the audience. The first thing you have to understand when you're talking to someone is who that audience is. And as academics, like, just a small example, we travel around the world, and sometimes we meet with people where the amount of communication that we can get across is very small. Like, it's a very tight channel, because of the language barrier or cultural barriers, and so sometimes things like jokes and sarcasm just don't work, whereas in other places it works very well. And if I go back to my small farming community, I would probably speak differently than I speak to, say, the executives at my university, right? So you kind of have to know your audience and be adaptable to what it is you think that they want to hear, and inject your message into what that is that they want or need to hear.
Behind you on your green stream, we see a tiny part of the universe. I presume that's just one of many universes. You also write about quantum consciousness and the more energetic parts of quantum physics.
Yeah, I think part of my writing about quantum mechanics is really just and the latest adult book that I wrote was secretly a way to inject some quantum physics into mainstream culture, because yeah, as you said, there behind me is a picture from NASA. I don't remember which direction of the sky it's pointing in, but when I approached the last book I wrote, it was from this lamentation that all scientific communicators, at least the ones that are popular, regardless of their training, end up showing pictures of space and talking about cosmology instead of, say, their area of expertise. And so lately I've been writing about how I think quantum mechanics is so important. It touches like every part of our understanding of the world, from cosmology down to the technology that we use to our understanding of consciousness and philosophy more generally.
And everybody in quantum knows your books. I'm sure that Denise will ask a lot of questions about that and your work. You also wrote a book, Blockchain for Babies.
Yeah.
Not gonna read that. Not sure why we're doing blockchain. But you wrote another one, 25 pranks.
Yes.
That sounded very interesting. What is a good physics prank to play on somebody in quantum?
It was actually a kind of the idea for writing the book was it was simple. I wrote it with a few colleagues, and we joke around, and we have fun with our kids. And when we sat down to start writing the book, we thought, oh, this is a bit dangerous to tell kids how to prank other people. So the pranks in the book they're a little bit tame, so they're not as exciting. Like, Netflix isn't gonna buy the rights and start start making a prank show out of these pranks. They're not like large and exciting pranks. But the point of the book was really to explain the science behind the prank. So it's a good question, like, what's a good physics prank? And the first prank in the book is simple. You take a bottle of water and you poke holes in it. And what will happen? In fact, nothing will happen, because the holes are small enough that the air pressure will keep the water in the bottle. Of course, until someone goes to grab the bottle and adds more pressure to the inside of the bottle, and all of the water starts squirting out. So that's kind of like one of the pranks in the book. They're all sort of using household items, and most of them are any mess involves just water. So we explain how to do the prank in the book, and then we talk about the science. So in that case, it's the science of air pressure.
Magic is a real thing. Before we get back to that, let's discover more about your work and your books. Denise, over to you.
Thanks, André. And I know my office is dark, but I have my display of Chris Ferrie books behind me. And then everybody in quantum computing knows this famous book, Quantum Computing for Babies. So, Chris, we're so delighted that you're talking to us. So thank you. As I was doing research on you, I noticed that you had a really great personal website and included things like resources, rants, explainers, some really great information that I hadn't seen about entry points for quantum computing. And I know a lot of people want to learn how to get started. And I was hoping you might comment a little bit on what your recommendations would be.
Yeah, that's a good question. In that particular blog post, I kind of laid it out in terms of where the you're currently at, right? So it really depends. If you're if you're a high school student and you just want to play around, there's options in terms of um, things like games. There's I think a really great one. I think it's just called Quantum Game, but it's about like photonics, and it explains quantum computing through like linear optics. And so I think for someone who doesn't have a lot of math background and just kind of wants to get the gist of it, these quantum games that are available are a great sort of start. The more and more there's courses that are becoming available. So Qubit by Qubit runs this online course. Those ones are a bit more challenging in that they're timed, so you have to be you have to sign up, and then not just like uh, on demand. Um, uh, Q Control is a company here in Sydney, but based primarily in Sydney, who have a product called Black Opal, which is like this. You think of it as like Duolingo for quantum computing. So I think these are great entry points for people who are kind of starting their journey. They don't yet have uh, they don't have any background. Um, if you've taken all the prerequisite courses, nowadays there are university level courses that you can take where you can get, say, a minor in quantum information theory. So at UTS, you can get a Bachelor of Computer Science and a minor in quantum computing, which involves you taking six subjects in addition to all your regular computing subjects that would get you the Bachelor of Computer Science degree. And of course, nowadays there are many many universities these more traditional sort of pathways. Now, those ones, I think, those get you a undergraduate degree in quantum computing, and at that point you can enter the industry, especially if you have a Bachelor of Computer Science and you know some quantum computing, then you'll be in high demand. If you want to go even further, of course, there's lots of graduate level courses as well around the world. And if if you're someone who has if you're a technical person, you have a job, and you're just curious in your spare time, you want to learn about quantum computing. Again, there's lots of open courseware, MOOCs and things that are on this topic. So in that particular blog post, I kind of list a few for these various different points at which you might enter the field.
That's great. I don't know about you, but that is one of the most common questions I get is, where can I start, and do you have a list? So I really thought you had a great comprehensive list. So thank you. Also on your website, you have a link to your publications. And recently you had a big publication in Nature, where I think it's a good example of how a theorist and experimentalist collaborate. Maybe could you talk about that, please? Tell us about that paper and the
Yeah,
work.
so that paper, it was one of three in that issue of Nature. So it's interesting, the cover for that issue was about just generally the three works, which all are about achieving high fidelity multi-qubit gates in silicon based or spin based qubits. And I collaborated with Andrea Morello's group at the University of New South Wales in Sydney, and how that came about was interesting. We were having a workshop about another grant, not on this topic, and so his group was there, and my group was there. We were at UTS and in some boardroom, trying to figure out how we're going to meet some milestones of some other grants. And at the end, he said, "Oh, I have this other problem. We're creating this. We have this really great 2-qubit gate, but we need to prove that it has 99.9% fidelity. How do we do that? Like, how do we prove beyond a reasonable doubt to any skeptic in the community how that this gate is 99.9% fidelity? And so at the whiteboard, I kind of explained some theoretical ideas about how we do characterization, in theory, as a theorist who typically think of like adversarial scenarios because uh, uh, there's nothing, there's no other sort of uh, stereotypical like situation that you can think of. So that seemed like the right thing to do. If you can if you can implement a protocol is designed to work in an adversarial scenario, then you should have beyond any doubt done the thing that you set out to do. And so we worked with him to design experiments that he would need to do, or his people in his group would need to do, and then the data analysis techniques to say with certainty that they created this 99.9% fidelity 2-qubit gate.
It was a great paper. It was a great issue of Nature. So really excited about the future of silicon. So I think your lab, though, you are also doing a lot of machine learning work and quantum data sets for machine learning.
Yeah, so lately I've been focusing on machine learning as a tool for characterization. So like the broadest picture is we want to characterize and control quantum systems, and machine learning seemed like a good potential avenue that was untapped. And I started working on this maybe 10 years ago now. And we cover lots of areas of machine learning. So there's just the idea that you have this problem. Machine learning encompasses a lot of solutions to problems. So let's try to apply those methods and techniques. So that's just classical techniques applied to data that's obtained from quantum systems. But there's also, the fact that, the quantum information is a different type of data. And so you can ask, well, what does machine learning look like for that new modality? You have this quantum data instead of classical data. So that's a different area that still kind of goes under this umbrella of the juxtaposition of the words quantum and machine learning. So I have students that work on a broad range of things, from just applying classical machine learning and control techniques to quantum systems, to ones that think about quantum data, like how do we think about quantum information and what you can do with it in the context of machines.
Thank you, Chris. I'm going to hand it back over to André, and hope that are you going to do the famous questionnaire?
The famous
looking forward to hearing
questionnaire,
that.
and of course a follow-up question first. You're calling in from Australia or maybe space. We're still not sure, but the quantum world is small. Australia has a very, very strong program with many well-known researchers and startups and well-funded. I'm from Germany. France is emerging. The EU flagship program. The UK doing very strong. Obviously, North America, Israel is emerging. What is kind of your view on international collaboration or lack thereof, hurdles? Australia made news 6 months ago with a ban on foreign direct investments. What's your take on the global quantum scene from down under?
Yeah, it's a good question. It's hard to say. Australia is famously like isolated, physically isolated. It's when we look at a globe, everything looks small and together, but especially nowadays, because of the pandemic and the travel restrictions that are in place, it becomes more and more isolating in Australia. And if you're like me and you've wisely chosen to turn off most of the news that gets exported from countries like the US and other places, then you kind of lose touch. You lose touch a little bit because you're not traveling around and meeting with your colleagues. And you're kind of limited to these virtual meetings. But just generally, you tend to collaborate with people that are in your proximity. So I worry a little bit for Australia that we are falling a little bit behind just because of this lack of connection that was was mediated through people traveling here and people within Australia going out and hearing about news firsthand. Um, yeah, so in some sense, I don't have really strong opinions about it because I have very little information. I Australia is one of the few, um, countries within these groups of 8 or 16 or 24, or however you want to count them, modern economies that doesn't have a flagship program. So, we're still limited in the amount of funding that's available here. The amount of academic research is the same, although many prominent academics have left Australia in the last 2 years to go work for companies abroad. Um, so yeah, within Australia, you could paint a pretty disappointing, or a pretty sad picture of our our future, given that we did have a very strong presence relative to the rest of the world, which seems to be weakening by the day. But of course, there could be an announcement tomorrow, so you never know. So
A
to be
little bit of
optimistic.
a warning call, but we'll try to remain positive, and I'll make a plug for One Quantum and Women in Quantum. We build communities all around the world, and we have many partners and members in Australia, which is very exciting. So we'll all try to contribute to that, and hopefully in person again soon. And now, as Denise promised or threatened, the famous Marcel Bruce James Lipton questionnaire. Chris, 6 rapid fire questions, and your job, if you accept, is to give 6 rapid fire, 1 word, 1 sentence answers.
I can do my best.
Let's go. We have 3 minutes. Who's your favorite scientist?
Albert Einstein.
Do you have a favorite entrepreneur?
No.
What is the quality that you desire most in a scientist?
Honesty.
Are there a lot of dishonest scientists?
Probably.
What do you appreciate most about working in quantum tech, for those that are honest?
The challenge, yeah.
Which quantum tech application, real or fictitious, computing or not, is your favorite?
I would say simulations of new and exotic materials and phenomenon.
Do you have a quantum dream?
A quantum dream? Oh, a dream for quantum. Yeah. Like maybe, like I said before, I dream that society could have a more complete and appreciation for quantum science.
That will still take a little bit of time. Do you have a quantum nightmare?
No, I don't think so. No.
First time that we have that. That's good. Last question. Imagine that tomorrow you wake up, you walk into your living room, and you have a universal fault-tolerant quantum computer sitting there. It's the first and only one in the world. Works at room temperature. You can't use it yourself. Who do you give it to?
I think I would destroy it.
Wow. Really?
Yeah. I was gonna say, I'll give it to one of my kids, but in hindsight, that's probably a bad idea.
Well, Chris, it was a pleasure to have you with us, calling in from the universe. Hopefully, we'll figure out our way in quantum so that we don't have to destroy that machine when we get there. And we sure are grateful that you didn't end up playing sports and video games in the heartland.
I still play a lot of video games.
Good, but you found your way into quantum. Thank you, Denise. Thank you, Atom Computing. Thank you, Chris. It was a pleasure. This concludes Season 5, Episode 5 of the weekly Quantum World Detangled. You are now detangled.